Hi everyone, and welcome to a new video about noise analysis, and this is our example number 1 about op-amp circuits. So we will discuss in this example op-amp circuit, which is a non-inverting amplifier, and we will look at our calculations and also the simulations in SPICE to verify our calculations. So let's look at our example. We have the following circuit given, which is a non-inverting amplifier. The R1 has a value of 820 ohms and R2 is 8.2 kilo ohms, and an op-amp X1 is OPA 209. So that is the circuit. We have the op-amp with the power supply given, and we have an input voltage, and we measure the output voltage, and we have two resistors. Okay, what is now the required values? We have the input referred RMS noise voltage, that is the capital letter E sub N in, and we would like to know what is the output referred RMS noise voltage, which is in the capital letter E N out. So those two we need to determine. So let's look at our step-by-step solutions. Before we move on, let's look at the op-amp specification in more detail, because that is the op-amp we are using, and that will of course determine what the output noise will be in a partial form. So let's look at our datasheet of the OPA 209. What we see is the following plot, which are the noise plots, so input noise voltage spectral density, and also the input current noise spectral density as a function, of course, the frequency. We also have the parameters for the open loop gain, the frequency response, and also the noise for several conditions. And we will clarify this step by step in the following analysis. So what we have is the DC open loop gain, open loop voltage gain, which is given by A sub OL, which is in this case 132 dBs, which is also seen here. There's also a separate plot actually in the datasheet of this op-amp. What we also see is the gain bandwidth product, which is a very important specifications, and that is then here 18 megahertz, which is actually shown here. So now the broadband noise voltage density, which is also called the white noise voltage density, is given by small letter E sub NBB broadband, which is then 2.2 nanovolts per root hertz, which is actually shown here, which is the units here. So this is the noise density, and it's the input noise voltage. We also have that actually in this plot. We can see that here, which is then the condition where the noise voltage actually is a constant, which is then independent of the frequency. There's also a dependent part, and there's an independent part. That's also valid for noise current. So the broadband noise current density, which is then again that constant value, is for the current 500 femtoamps per root hertz. And that can be also seen here in this plot, which is then 0.5 picoamps per root hertz, which is then equivalent to 500 femtoamps. What we also have is the region where the frequency will change your density of your noise. So it is 1 over f noise voltage density, and that at specific frequency, for example at 0.1 hertz, is given here. It's 20 nanovolts per root hertz. It can be seen also here. We also have it 1 over noise current density at the same frequency, which is 0.1 hertz, and that is given by this symbol, which has a value of 3.75 picoamps per root hertz, which is then also shown here. And those are important values we will use later on. Okay, let's move on and look at the circuit performance. What we have for this circuit. We have the gain, and actually we have two gains. What's called the closed loop signal gain, which means actually the gain where we increase the gain of the signal. So this value will be used to increase the actual gain. And we have also the noise gain, which means actually that the noise will be multiplied by this number. Now the signal gain is actually looking at your input signal, so input voltage in this case, and what is an output voltage as a signal depending of course on the configuration around this circuit. Now in this case we have a non-inverting amplifier. We know there's 1 plus the feedback resistance divided by this resistance, which goes from the inverting node to the ground, which is then 1 plus R2 over R1, which is a very familiar formula for this. And we have the 1 plus the 2 resistors in the ratio, and we have then 11 as our signal gain. The noise gain as a definition is in this case exact same, but it can be different for the different circuits. We will always look at the non-inverting input of your op-amp and then determine the gain respect to actually looking at the output. So in this case it is exact same because the signal is also at a non-inverting input. So in this case it's just exact same expression, and also the value is exact same. So the noise gain and signal gain are both 11. We also have a very important parameter, the bandwidth, the frequency performance, which is then in this case we just start with the closed loop signal bandwidth. We also have the closed loop noise bandwidth. So similar to the gains, we also have the noise and the signal bandwidth. So those are given by the following expressions. The signal bandwidth is actually determined from the gain bandwidth product. It is actually a product of the gain and also the bandwidth. So once you know the bandwidth of your circuit and you divide it by the noise gain, you can then use the gain bandwidth divided by the noise gain to determine the bandwidth of your circuit. So this will be the 1.636 megahertz will be the bandwidth of our circuit. So if you have of course low pass filter, this will be your cutoff frequency. And noise bandwidth will then be determined shortly, and we will see how we can do that. We have in this circuit just one op-amp, and there are no other active or reactive components that will then increase the order of the circuit. Now, one op-amp, and we just assume, of course it's just an assumption, that this op-amp will behave as a first order system, which has only one pole, which is then this cutoff frequency. Now for that, we then say it is a first order system. We can then use the conversion factor going from the signal bandwidth to the noise bandwidth, which is this value. I won't drive this, I won't prove this value, but if you want to go from the signal bandwidth to the noise bandwidth, you need to use this value. So the closed loop noise bandwidth for the circuit then is given by this expression, which is then noise bandwidth will be then this conversion factor times the signal bandwidth. So you will have actually a larger value for your noise bandwidth. It will be in this case 2.57 megahertz. You will need to use this value for the calculations in your noise. Now for the total noise voltage, means actually total noise voltage at input and also the total noise voltage at the output, we will look at the input referred RMS noise voltages and also the the total output referred RMS noise voltage, which are of course the required values for this exercise. Now from these we can of course also determine that using this formula. You can also say the output referred RMS noise voltage is then equal to the noise gain times the input referred RMS noise voltage. So the input referred RMS noise voltage is composed of 3 parts. Now let's look at it in more detail by using also this model, because I have now added for this op-amp 2 sources, and these sources are modeled using the datasheet of this operational amplifier. What we'll see actually is a current noise, so noise current generator here, just actually from this op-amp, and also the noise voltage generator here, which models actually our circuit. So this is in total in the op-amp itself. So this is now a noiseless op-amp, and in this case this is of course a op-amp with a noise, and we have now a noiseless op-amp with 2 sources that will be used to determine the output noise and also the input noise. So we have then the input referred RMS noise voltage that can be due to the internal op-amp noise voltage. That is this one. So that is actually given by this expression, which is then the source to model the noise voltage. And that's given by capital letter E sub n, which is then the noise, and then the small letter v for the voltage noise. The second one is the input referred RMS noise voltage due to the internal op-amp noise current sources. So in this case then, this, what kind of effect will this for noise have at the input of your op-amp circuit? And finally, we'll have the input referred RMS noise voltage due to the resistors. We have, of course, all the resistors here, and we have seen in the previous examples in passive circuits that also the resistors will generate noise, and it will be, of course, a white noise in most of the time. So we will use, of course, these three parts to determine then the input referred RMS noise voltage, and then from there we can then determine, using this formula, the output referred RMS noise voltage. So the input referred RMS noise voltage is then calculated using the root sum of squares. And what does actually that mean? It's the following. You have then the input referred noise voltage, and you will add these parameters, first square them each separately, add them up, and then take the square root. We actually have done this in the previous examples. That is, of course, needed in the noise analysis also because we are working with factors. So that's actually what we need, and we need actually three separate parts to calculate. So let's look at it in more detail. Step one is the input referred RMS noise voltage due to the internal op-amp noise voltage sources. So we actually start with this one and then actually ignore the rest. So we just assume that there are no noise current source of the op-amp. So the noise voltage source of the op-amp on its own is also composed of two parts, which is the broadband noise, which is actually the white noise voltage, and we also have the 1/f noise voltage. We have seen that in the plot also in the previous discussion, where you see actually a part which is dependent on the frequency and also a part which is then independent of the frequency, which is very similar also for the current noise. So the noise voltage due to that noise voltage source of the op-amp again is calculated by the root sum of squares, RSS, which is then given by this expression. So if you want to have the noise voltage, which is an input referred noise voltage, due to that noise voltage source of the op-amp, you need to take the square root of the square of your broadband noise voltage plus the square of your noise 1/f noise voltage. So let's look at the first one, the broadband noise voltage. How can we determine that one? That will be determined by using noise voltage, input noise voltage spectral density, and multiply it by the square root of your noise bandwidth. So we know what the signal bandwidth was. It was calculated by this expression. It was 1.636 megahertz, and we also have determined the noise bandwidth, and we also have the values here for your op-amp specification for future reference. And we had a noise bandwidth of 2.57 megahertz, which is of course larger than the signal bandwidth because there is conversion factor due to that conversion of pi/2. So the noise bandwidth, using that noise bandwidth and also the noise spectral density at the input, we can then calculate the broadband RMS noise voltage, actually this one, and it will be just using the 2.2 nanovolt per root hertz for the broadband noise voltage spectral density times the noise bandwidth square root of that one. That will give you approximately 3.527 microvolts RMS. In a similar form, we can calculate the 1/f noise voltage, of course input referred, but the formula is a little bit different. It's not the square root of the noise bandwidth. It is a normalized value for your noise voltage spectral density in that region of the 1/f noise, and we take the square root of the natural logarithm of the ratio of these two frequencies. So what are these? Let's look at it one by one. This FH is actually called the noise bandwidth of your system. So it is actually the higher upper cutoff frequency. It's also similar to that one. We also need the lower cutoff frequency actually, which is this one, and that is also determined from the datasheet. So it is the selected, again, it is a frequency which you can select from the datasheet, and that will be the normalized 1/f noise voltage. And we will see what we can select from the datasheet. And most of the time, actually, I already said that also in the previous discussion, we will take for f sub L 0.1 Hertz. But any value will do the job. So you can also say I will just take 1 Hertz or 0.01 Hertz. So how we can calculate then the normalized 1/f noise voltage, which is then E sub f norm. That is given by this expression, which is then this value, which is actually shown here. So this 20 nanovolts per root hertz, but it is valid at 0.1 hertz. We have seen this, of course, in the previous discussion when we saw the graph, which has the frequency dependent part and also frequency independent part. So if you do the math here, just substitute the values for this, which is then 20 nanovolts per root hertz. At that frequency, you will get 6.325 nanovolts RMS. Of course, if you look at a diagram in a graph and you will use 1 hertz, of course this will change, but your result will be then exactly the same. So that is, of course, why this is called a normalized 1/f noise voltage. Then using this formula, we can then calculate the 1/f noise voltage, which is then referred to the input, which then just substitute the values for this one, and also using the formula here by having the noise bandwidth here and also the 0.1 hertz here as, of course, the selected frequency. If you do math, you will get 26.30 nanovolts RMS, and that will be then equal to in microvolts RMS to this value. Now we have two separate parts of our input referred RMS noise voltage due to that internal op-amp noise voltage. Then we can use this formula. So using the RMS noise of the broadband part and also the 1/f noise, we can then calculate this. So just again using the root sum of squares, we have this expression, and if you look at this expression, you will see that this will also be very close to that value. And this is then saying actually that the dominant part here is the broadband noise voltage, which is most of the time also the case, but you know, of course, just calculate everything and then see later on which part is dominating. And in this case, this is definitely much larger than that one. And in some cases, people use the following rule of thumb. If this value or one of the values is at least 3 times larger than the others, you can actually assume, it will be a shortcut calculation, that this is then the total value for this expression. But in this case, I just did the math, and you can also see that this is indeed correct here. So let's then look at the next one, which is then the input referred RMS noise current due to that internal op-amp noise current source. So we will then look at this, which is of course our noise voltage, and we will need then the op-amp noise current. So this is then calculated using the equivalent resistance and also the noise current of the op-amp. So we will use this, but we will also look at what is the resistance we see at the node here when we, of course, disable all the rest of the sources. That is actually what's called the R sub EQ. So this is the resistance seen by the noise current source of the op-amp, and the value of the R1 and R2 in parallel will be then this equivalent resistance. So the value then can be calculated using Ohm's law, just the current times the resistance, which is shown here, and the IN is then on its own also composed of 2 parts. It has a broadband noise current, and it also has a 1/f noise current, which is actually similar to the part with the noise voltages. So IN is calculated using the root sum of squares, and again we have the very similar expression here. Now let's look at the white noise part, or what is actually the broadband noise current, which is again very similar formula, and we will use then this 500 femtoamps per root hertz and also noise bandwidth we have determined earlier. So we have the single bandwidth, and from there we have the noise bandwidth, again the same value, 2.57 megahertz. You just substitute the values and you will get 801.6 picoamps RMS. Now for the 1/f noise current RMS value of that one, I have a similar expression, which is then very similar to the voltage also. So this is then for the current 1/f noise current RMS value. You will have this formula. Again, we have normalized value, we have the upper and the lower value of our frequency. Again, this is the closed loop noise bandwidth. We have also the selected frequency for the normalized 1/f noise current, and we will use the datasheet for that one. And again, we use most of the time 0.1 hertz as the frequency for selection, but any frequency will do the job. If I now look at my op-amp specification here on the right side, I can say what is then the normalized noise current here. That is of course determined by this expression, very similar again to the 1/f noise voltage. You will take this value from the op-amp specification, which is then 3.57 picoamps per root hertz. You multiply that by the square root of the f sub L, which is then in this case 0.1, and you will have 1.186 picoamps RMS. And that will be then used in this formula, and we substitute in here this noise bandwidth, and here is 0.1 hertz. So we will have then this expression. And this is then very close to 4.898 picoamps RMS. Now we have now the necessary elements for the I sub n, which is then the broadband noise current and also the 1/f noise current. All them together, you just substitute in this expression, you will have then the following situation. So using the RMS value of the broadband and also the 1/f noise parts for the current, we have then this formula. You just substitute the values we just determined, and you will have again that this will be dominating. Why? Because if you just do the math here, you will again see that the broadband part is almost the same as the effective value for the complete noise current value in RMS. So this is again much larger than the 1/f noise part, so that will be of course also now dominating here. Now we will now determine also the equivalent resistance seen by this noise current source. This is the parallel combination of the R1 and R2. If you do the math here, you will get very close to 745 ohms. Now if you use Ohm's law, as we also already said in the beginning, you just have the noise voltage due to the noise current source of your op-amp at the input, and also the resistance, the equivalent resistance. So if you do the math here, you just calculate it out, you will have 0.6 approximately microvolts RMS, and a little bit closer is then 0.5976 microvolts RMS. So we have actually also the second part of the input referred RMS noise voltage. So the next one is the input referred RMS noise voltage due to the resistor. So actually the resistors in this case. So that's given by E, capital letter E sub NR. So we will calculate this using the white noise or the thermal noise formula for resistors. And we have seen this of course in the previous examples where we discussed the passive circuits. So the equivalent resistance again is seen at the input nodes of the op-amp. And in this case we have just one. There are two resistors here at the one node here. And at this node we have actually no resistors connected, because this will be a short for the analysis when we only look at the noise. So again, we only have the R1 and R2 in parallel. This is then given by this formula. So the thermal RMS noise voltage for resistors is given in general by this expression. You all know that, which is the very familiar formula to calculate the thermal noise of a resistor. And then we have the following parameters. We have the K, which is the Boltzmann constant, which is given by this value, approximately 1.38 times 10 to the power minus 23 joules per Kelvin. We have the temperature, absolute temperature in Kelvin. And for room temperature, which is of course a bit hot room, 27 degrees operation, we use, I will use always, most of the time of course, the capital letter T is 300 Kelvin. You will see also in different analysis that this is a little bit smaller, maybe a little bit larger, but it really depends on the operating frequency, operating temperature. The R in this formula is actually the equivalent resistance in ohms seen at the node. So this will be of course also used, and then noise bandwidth, NBW, is then what you need to insert here, but in hertz. So in our case, for this circuit, the R is actually our equivalent resistance, which is then 745 ohms, and our noise bandwidth is then 2.57 megahertz. So we actually have the necessary elements here. We know the temperature. We also know the Boltzmann's constant. So if I now just substitute everything in it, I will have then, for my value of the terminal noise voltage, RMS, for my resistors, of 5.616 microvolts RMS. So the total input referred RMS noise voltage, which is then this one, will be then calculated using again root sum of squares, because we have now all three elements for this input referred RMS noise voltage. And this was a formula, again a reminder, and then looking at several parts, which is then the input referred RMS noise voltage due to the noise voltage source of the op-amp only. This is the input referred RMS noise voltage due to the noise current source of the op-amp only, and this is then the input referred RMS noise voltage due to the resistors only, which is then R1 and R2. So if you collect them, just substitute in this expression together, you will have this, and if you calculate it out, you will get, for the input referred RMS noise voltage, will be then 6.66 approximately microvolts RMS, or a little bit close to 6.659 microvolts RMS. Now we have the total input referred RMS noise voltage. Now the next step is a little bit easier, to go to the total output referred RMS noise voltage, which is of course also the question in place in this exercise. We use the closed loop noise gain, NG, which is in this case 11, which is of course equal to the signal gain in this example specifically. So the input referred RMS noise voltage was 6.659 microvolts RMS, and if I now use these two values for my output referred RMS noise voltage, I say noise gain times the input referred RMS noise voltage will be 11 times this value we just determined, and that will give you 73.24 microvolts RMS, and that is what we have in the output. So my input is this value and my output will be 11 times larger, and this is actually after integration in frequency. Of course, we will verify this in the simulations. But let's also look at the signal noise ratio, which is a very important parameter, SNR, and we will look at it in more detail. What is SNR? Let's also remind that here, signal to noise ratio is a measure that compares the desired signal level to the noise level. So we would like to measure and make a ratio between these two levels. So we know, of course, that it is defined as a ratio of signal power to the noise power. So it is then often also expressed in the units of dBs or decibels. So if you have a ratio which is larger than 1, means actually greater than 0 dBs, that indicates you have more signal to noise. And if you have a smaller value than 1, between 1 and 0, then you will have negative value for your dBs. That indicates that you have less signal than noise, or you have more noise than signal. Of course, we want to increase the SNR, so we'll optimize for having a large SNR. That will of course have better accuracy and also better performance for your circuit. Now for this circuit specifically, the SNR at the output for a specific frequency can be calculated using this expression, which is then already given in decibels, dB. So it is then 20 log of 1 over that total output referred RMS noise voltage, and that was actually calculated here as 73.24 microvolts RMS. If I now calculate the SNR now using this value for the output referred RMS noise voltage, I have this. You can see it is now 82.71 dBs. That is our SNR value for the output for this circuit, and we will also verify this value. So let's look at the simulation results step by step. We just first start with the frequency response and specifically also look at the bandwidth. So this is the circuit and this is the body plot, just looking at the gain and also the frequency from 1 Hz all the way to 1 GHz. So that's actually the large span. What you see is actually the DC gain here is 20.83 approximately dBs, and we have a cutoff frequency is 1.626 megahertz. And what we have calculated was the following. So the DC gain here I can read from this graph, and if you now convert this to a scalar value, it would be 11. So that's actually also our signal gain. So this is actually the formula for going from the dBs to a scalar value for your gain. The cutoff frequency, the bandwidth, actually in this case, because this is a low pass filter action, that will be then signal bandwidth is then gain bandwidth product over the noise gain. Now, if you now do the math here, 18 megahertz over 11 was 1.636 megahertz, and I have here in the simulation 1.626 megahertz, which is very close to the calculation. So the model of this op-amp and also the calculations do match very well. What you also see, I have also placed some extra labels here that you can see that this is indeed a first order system, because that was our assumption. Now, if I want the first order approximation to be valid, I need a slope here, which is then minus 20 dBs per decade. So I can check that. For example, this is at 10 megahertz. I have approximately 4.94 dBs here, and I need actually a decrease of 20 dB going down if I increase this by 1 decade. And this is actually a minus here, so you cannot see it because of this. So if I just move this back, you can see this is 4.94 dBs at 10 megahertz. If I go 1 decade with my frequency to 10 times, this will be 100. We'll see it is the minus 14.95 approximately. So we'll have a decrease of 20 dB here. And again, another check, 10 times larger frequency. So we go from 100 megahertz to 1 gigahertz. I now go from minus 14.95 dB to minus 34.96 dB. So it's very close to a first order system, because I decrease my gain by 20 dB for each increase in the frequency by 1 decade. So that's actually what we have here. So the next is the input noise voltage spectral density, which is then this plot. You can see, and also we have seen this in the datasheet of the op-amp, that the first part is frequency dependent. So the input noise voltage spectral density, it is dependent on the frequency. So for each frequency you have a different value. So at 0.1 you can see then there's approximately 20, which is actually what we have used, 20 nanovolts per root hertz. So it's very accurate. And you have also the part which is actually a little bit independent of the frequency. And of course you have some value which will go up here. That is actually another modeling, but we don't bother about that part. So that means the frequency dependent part is the 1 over F noise, and frequency independent part is the broadband or the white noise part, which is actually this one. And what you see is then that is then 4.2 nanovolts per root hertz actually here, and that will be always the same no matter what the frequency will be. So approximately at 100 hertz, and will stay constant up to approximately 300 or 400 megahertz. If I now look at the output noise voltage spectral density in a similar form, you can already see that it's of course larger than input noise voltage spectral density. But again, we have the 1 over F noise part and also the part which is then a constant, which you also see, which is interesting because that is not what we had in the input. This value will approach a 0 for larger frequencies. Why? Because the input is just actually the input of your circuit, which is of course frequency independent for very large frequencies. But this part, the output, of course, is after the action of the op-amp. So the op-amp, we already have seen that in the previous analysis, and also the simulation results of the in the frequency response of the bandwidth. we have seen that at some frequency it will decrease the gain. And that will of course decrease also the noise gain. So you can also really see this approximately 1.6 megahertz here. So that's actually one part which is then 1 over f noise, and you have a part which is then constant, and then you have a part which will then decrease and then go all the way to 0. So we actually have 3 parts here. So you have a frequency dependent part, which is the 1 over f noise, frequency independent part, which is the broadband or the white noise, but you have also the output noise that goes to 0 due to bandwidth limiting of your op amp. So this is actually only valid for the output. So let's also look at the total RMS output noise voltage, which is very important of course, and this is again the system or circuit, and you can see that this plot will go up and then it will approach a constant value, so it actually saturates after, let's say, 1 gigahertz at 73 microvolts at this frequency of 1 gigahertz. And this is our simulation result. And the calculated value was also 73 microvolts RMS, very close to that one. And the simulation is also the same. So this is a very nice result. So we have actually a confirmation of the calculated value and also the simulated value. So that is very, very nice to see that the calculation and also the simulations do match very well. The calculations actually were 73.24, but this is very close to that one. So let's also look at the signal to noise ratio. This is the signal to noise ratio plot. You can see it starts off very large at very small frequency, so about 1 hertz, and all the way to 1 gigahertz we have the plot of the SNR, which is then the signal to noise ratio here, the frequency there. It actually settles down at some value, which is done here, 82.73 dBs. We have this formula for the SNR, we already discussed this, and this was our output referred noise, RMS noise voltage in more detail here, so a little bit accurate value, 73.24 microvolts RMS. And if I now substitute in here, we have determined that was 82.71 dB. And I have here, this is the calculated value, and I have in a simulation 82.73 dBs, which is very close to the calculated value. It's actually a very nice result. So that will also confirm our calculations. So this is actually also for the noise voltage and also for the SNR. So now we will look at this analysis also in the SPICE simulation, and we will see how we can generate these plots also in the SPICE. So you can also see how I do that, and that will be helpful for you also for making a noise analysis and then other circuits. So let's jump to SPICE and see how we can generate these plots also there. So next step is SPICE analysis. So this is our circuit in the SPICE simulator. We have the R1 and R2 in our op amp, and we have the 2 noise sources which will model the noise current and also the noise voltage of the op amp. So if I now double click on this one and go to the enter the macro, you can see several values like the 1 over f noise frequency, which is at 0.1. What the value of that one is, that will be also used of course from a datasheet. So we will enter these values in this using a datasheet, and this is actually a model which is generated or provided by a text instrument. So I have used this to generate actually and use that as a model for the noise voltage. So if I close this, you can also see other values like a formula, which is of course not really interesting here, but this will do the job, and also goes to the actual value of the 1 over f noise at 0.1 hertz, which is then 20 nanovolts per root hertz, and also the broadband noise value. If I close this and also look at the noise current, again enter that one, you can see it was it's actually 3750 here for 1 over f, and this is given in femto amps, so it is then 3.75 picoamps, and again at this frequency. It's very important. And you have now here also in femtoamps is 500 femtoamps for broadband region. And again, we have some formulas which is now not really important for us. We only need actually three values we need to enter in this micro, which is then these two for the 1/f part and also for the broadband noise current. So that's what we get from the noise current and noise voltage models for our op-amp. So if I now do the analysis and go to noise analysis, I can now generate the plots. And of course I again plot from 1 to 1 gigahertz, and this is the number of points to make it accurate. And I will have an output noise, input noise, total noise, and also the signal to noise ratio. So the input noise will generate the input noise voltage spectral density. Output noise will then generate the output noise voltage spectral density. This will be a total RMS noise voltage, and this will be the signal to noise ratio. So let's run this and see what we get. Okay, this is the plot, and the first one is the output noise voltage spectral density, and you can see again it starts off very large and then goes down, and it will approach zero for very high frequencies. So it is very close to what we had actually in our analysis. You can also look at the input noise voltage spectral density, and for 1 giga it goes a little bit up, but you can also see that this is for very small values. It starts off large, but you can also see what will happen if you, for example, look at 0.1 hertz, which is of course not seen here. So if I want to look at the 0.1 hertz, that is of course not visible here because we need to plot this also for 0.1 hertz. So let me also do that one, and then generate the plot again, because that was actually the part where we have the 1/f noise part. So let me generate this, and it will give the plot again. So we have the plot, and that is then the plot here. And if I now look at the input, of course the second input and second output, so you can see it is very close to 20. So we have used actually 20, it's now 20.5. So it is actually due to that modeling. And if I go down for broadband value, it is then 4.15, and it will approach that value or stay at the value approximately that value up to, for example, here 200 or 180 megahertz, and it will increase a little bit due to the other effects in the op-amp. And if I also look at the total, noise voltage, you can see it will approach 73 microvolts RMS. So let's run this and see that indeed it is going to that value. The signal to noise ratio also starts off very low, very large, but then it settles down at this value. So it is 82.73 if you go to very large frequencies. You can also generate the Bode diagram to see that indeed it is it has exactly the same gain, DC gain, and also the cutoff frequency. So you do analysis, AC analysis, and go to the AC transfer characteristics. And again, you can do from 0.1 to all the way to 1 gigahertz. And I will just plot the amplitude. So I will just run this, and we will generate the plot. So that is our plot for the Bode. And you can see it starts off at 20.83, which is then very close to 11 as a scale. This is the dB, and this is the frequency. So at 0.1, it is then this value, which is then converted to scalar value, which will be then 11, what we had actually as our signal gain. Now, if I do now this, and I will go to the cutoff frequency, which is then of course 3 dB down, or 3.01 dB, 3.01 dBs, I can of course go down and then say, okay, I will need to of course make this 81 to have it exactly, or 82. Then you can see it is then 1.63 megahertz, which is then actually this frequency. So that is also what we had. We had 1.636 megahertz as our calculated value for our signal bandwidth. So that is also in confirmation in the simulation for our circuit. So this is on our noise analysis for this example, having a non-inverting amplifier, which we have then the modeling of our op-amp. So I will close this. You can see that it will be a model of an op-amp, and we have two resistors, and we have calculated the total RMS noise voltage at the output and also total noise voltage at the input in RMS values. And we have then seen step by step how we can determine these noise voltages by using the sources of the op-amp model and also the noises due to the thermal noise of the resistors. So this is our example number about the active circuits and specifically the op-amp circuits. We will continue in a different example, example number 2, with different circuits to elaborate on this topic in more detail. So if you have any questions or comments about this exercise, please let me know and I will try to answer them as soon as possible. Thanks again for your attention and see you next time. Take care.